It's pretty.
Should we get going? Okay. Well, welcome everybody here and virtually. I'm Jeff Gansel, I'm WASI's secretary. And want to talk to you with Lori as well about DIY observing of space weather. But I first want to start with kind of an apology. I'm one of these people, I detest cell phone calls. Absolutely detest it. It gets in the way of everything. But my daughter-in-law is in the hospital giving birth at this moment. I may have to take 5 minutes so that you will deal with me. Anyway. So the space weather is all about the solar wind. You know, the sun is constantly throwing this wind of charged particles at us, you know, protons and electrons. The sun itself is, we take it for granted. It's a very complicated system. I mean, you've got the core in the middle of it. That's about the inner 25% of it, which is where all the good stuff is happening. That's where fusion is happening. The rest of the star, nothing's going on, basically. There's no real chemical reaction. There's no fusion going on. But in the core, that's about 15.7 million degrees Kelvin. That's like maybe 30 million degrees Fahrenheit. And that's hot enough so that helium can come together and fuse, hydrogen can come together and fuse into helium. And what happens is the resulting helium weighs a little bit less than the incoming hydrogens. And that difference in mass is converted to energy. And good old Einstein, you know, taught us energy equals mc squared. And the mass that's lost is really, really small. But c squared, speed of light, 300 million meters per second, squared is a big number. And so a ton of energy is produced. And eventually that energy percolates up to the surface of the sun. And, you know, we get, of course, what we see, the visible light, of course, but there's an awful lot of other stuff coming out. Infrared radiation, you know, you go out in the sun, you stick your arm out from the shade, you put it out into the sunlight, and you can feel the heat. Well, your arm is really an eye. It's detecting the same thing your eyes are detecting. It's detecting the electromagnetic radiation from the sun, the light. It's just it happens to be in the infrared wavelengths. And it's producing a lot of other things too. The sun loses about 1.5 million tons per second of mass to the solar wind. These protons and electrons that are being thrown at us. Think about 1.5 million tons per second. It's been doing that for 5 billion years. I mean, this is a big old hunk of, you know, burning hydrogen. There's a lot of it there. And that stuff is coming at us at something like 500 to 700 kilometers per second. So, I mean, it's moving at a pretty good clip. But when it gets to us, there's not a whole lot, you know, it works out to be around 5 to 10 particles per cubic centimeter, you know, something like that. So it's a really good vacuum. It's probably a better vacuum than we can actually create on Earth. But that's per cubic centimeter. The Earth is big. There's a ton of this stuff hitting us. And so on a really good day, like we had this past October, you might get an aurora. Those are those particles coming in and hitting our atmosphere. One part of the interesting things is the solar wind is coming off and it's hitting the Earth's magnetosphere. The Earth, of course, has a magnetic field, thankfully, because otherwise we'd have a hard time navigating without our compasses. But it's shaped by this incoming wind. And you can see, look at the shape of it. It's not like a sphere like you might expect. It's got this cone going out behind the Earth. And it's entirely shaped by these incoming particles.
But it looks like an arachnid.
Like what?
An arachnid.
An arachnid? Like
A
spider?
Yeah.
That's sort of, doesn't it? Yeah. Well, we could do sort of an evil version here, like a horror movie version. If you turn the sun off, the magnetosphere would look like a sphere, but it is entirely shaped by this incoming solar wind. You know, if we didn't have a magnetosphere, there would be no life on Earth. because these incoming particles would zap us. You know, we're in this golden zone. If we didn't have the magnetosphere, we wouldn't be here. If we didn't have the ozone layer, we wouldn't be here. There's a whole bunch of influences that have come together to make life on Earth possible. Look at Mars. Mars has no magnetosphere, and it used to have an atmosphere. Most of that was stripped away by the solar wind, because without a magnetosphere, there was nothing to protect the planet. And so I know there's a lot of talk about, you know, sending people to Mars. One of the big concerns is without that magnetosphere, the astronauts would be bombarded by these highly energetic particles. There's an whole saying: if the sun sneezes, the Earth catches a cold. Because the sun is very dynamic. I mean, look, you can see the solar flare coming off. There's all kinds of things going on. If you look at the sun through its solar telescope, you'll see all the sunspots and flares and whatnot. It's a very active and dynamic environment. So this is a typical flare. You see here, that's not where the Earth is, but this is how the size of the Earth, what the size of the Earth would be compared to the size of this flare. I mean, we're like a little teeny bugs in the solar system. The flares are much more enormous than even the entire Earth. Where does this stuff comes from? The sun has its own magnetic environment. It's very complicated. You know, the sun revolves about every 25 to 30 days, depending upon the latitude. It revolves at different times, depending upon what latitude you're looking at. And as a result, the magnetic fields get all twisted up and do crazy complicated things. So here's where a flare comes from. You have this magnetic field at the surface of the sun, and some of the magnetic field is forced up above the surface of the sun, and that drives these particles to come up to follow that field. Oh, and please feel free to jump into questions at any time.
Yeah.
Yeah.
In terms of the chemical processes that are going on in the sun, I think I remember in one of our earlier lectures that lithium is also formed in that chemical environment. Is that true? Lithium does exist in the photosphere of the sun?
Yeah, you know, with the Big Bang, the Big Bang created a bunch of hydrogen. About 3/4 of the universe was hydrogen. Helium, about 1/4 of the universe was helium at that point. And a tiny bit of lithium, about that much lithium was created at the Big Bang. But during solar dynamics, as the sun fuses hydrogen into helium, some lithium is created as well. But also, I mean, the heavier elements are created. I mean, our sun will eventually turn into a white dwarf, composed mostly of carbon and oxygen, because those are being manufactured by the fusion processes. And our sun isn't big enough to do anything more than carbon or oxygen. It's not massive enough. And so it will turn into a white dwarf in about 5 billion years.
And be producing carbon and oxygen.
Well, it will, by the time it's produced those things, it will essentially go dead because it can't fuse anything heavier. If you take a huge star, a much more massive star, they can produce much heavier elements. But it takes some to produce, to fuse hydrogen, which is what's going on now. You need about 15 million degrees of temperature. To fuse helium, you need about 100 million degrees. To fuse into the carbon, you need almost 1 billion degrees. And so to go to the really heavy elements, you just need a massive, massive star. And our star is pretty, run of the mill. It's not that big. So these are photos from various space observatories. And in the middle here, you see this disk. That's a coronagraph. It's just as blocking the sun because the sun drowns out everything. You can't see anything if you're looking right at the sun itself. But it's showing these flares and coronal mass ejections coming off of it. And if you consider this, the sun is about 850,000 miles in diameter, which is that much. And look at this flare coming out. Look how much bigger it is. It's an incredibly dynamic environment. No one knows how much stuff is ejected from the sun. It's thought that it's somewhere around 1 million tons a day is actually ejected into space from these things. And these coronal mass ejections, fortunately, I mean, they're very, very violent. Very few of them actually hit the Earth. You know, the sun is a sphere. It can eject stuff in any direction. We're this little old Earth over here. To get hit by one is pretty unusual. And we'll talk a little bit more about that later. But on the average, it's like 6 to 10 of these ejections happen every day.
Jeff, so
Yeah.
that the mass from the CME is in addition to the normal stuff that comes up.
Exactly.
Okay.
It's a lot of stuff.
Yeah.
Well, the sun, as I recall, I think it weighs 2 times 10 to the 30th kilograms. And the Earth is about a third of a millionth less than that. But you put a third of a million Earths in the mass of the sun. So I mean, it's a big, it's a very average star, but it's a big sucker. This is looking at it from a sort of grand perspective. The sun in the center, the Earth is out here somewhere. Neptune is here. Neptune is 30. An astronomical unit is a distance between the Earth and the sun. That's about 93 million miles. Neptune is about 30 astronomical units, AUs out. The solar wind goes out way past that. Goes out to these very distant places where only in the last a year or two, the Voyager spacecraft that have been traveling since the 1970s have passed out past where the solar wind can be detected. They believe it extends out to about 100 astronomical units from the sun. So that's like 3 times the distance to Neptune. And, you know, we think of Pluto, no longer a planet. Pluto is almost the same distance as Neptune.
Are Voyager 1 and 2 still conveying stuff back to us now or not?
Yeah, I can't remember which one had a bad summer. They had they lost communication with it, but it came back online. They use radioisotope sources to generate electricity because there's no sun out there. You can't use solar cells. And those isotope generators, they have a half-life as the uranium decays, and they're running out of power. So they keep shutting instruments off, but they're still getting data from some of the instruments. And when you could think about it, these were designed to last for a handful of years. It's been almost 50 years.
60s and 70s technology.
I mean, I'm a retired engineer, but all I can say, man, those engineers rock.
It was designed for how many years?
Like 6 or 8. They were just going to go out to Neptune.
Yeah, Voyager 1, I had to research this for the Global Star Party. Voyager 1, it needed to survive to get past Saturn.
Okay, so Saturn
That was the
is
research.
10 astronomical units. They are currently out at something like 50. That's cool.
It is very cool.
Got our money's worth out of that.
We got every penny worth. And what about the pressure? How much solar wind are you getting out at 100 astronomical units? And I actually looked it up. Once you're even at our distance from the sun, the pressure is about 1/1000th of a Pascal. Well, what's a Pascal? Earth's atmospheric pressure is 14.7 psi, right? Everyone knows that. But in metric terms, it's roughly 100,000 pascals. And the pressure that the Earth feels from this is on the order of a couple of billionths of a Pascal per square meter. But then the Earth is a lot of square meters. There's a lot of stuff coming in at us. So even though the pressure is almost undetectable for any sensor you could put out there, there's a lot of stuff hitting us. You know, we're talking about solar wind, you have to talk about comets. You know, one of the things we love about comets are the tails. Well, where do the tails come from? You know, as a comet approaches the sun, it has the heating effect on the comet. The comet is just basically an ice ball, snowball. And you often get 2 tails in different directions. You get one tail, which is just behind the comet, what you would expect if you're driving some big old monster truck that's spewing out, you know, all kinds of, you know, diesel exhaust stuff. It comes out right behind the truck. That's from the direction of motion. There's the other tail, which is as a result of the solar wind beating on the comet, pushes the comet's particles off exactly in the same line as the direction from the sun to the comet to the tail. And so you get the ion tail tends to be driven by the solar wind. So the sun is gonna be right here, and then the direction of motion is that way, and that's the dust tail that you get. It's not often that we can actually see both of them, but they're usually both there. Okay. So when we talk about solar weather and solar wind, how do they measure it? Well, there's a number of different metrics. Something that's really common is the KP index. Hey, I had to look that up. What is that K? It's a German word meaning Kennziffer. It means characteristic digit. But the KP index is something that they use to get a sense of what the strength of the solar wind is on Earth. And here we see there's one site, spaceweatherlive.com is a great site if you want to know what's going on right now with the sun. And here it shows a KP index of 4, which is not a particularly high number. But they also measure this in other parameters like A, B, C, M, and X. If you get to X, we're being hit hard. I mean, there's a lot of stuff coming in. You want to go outside at night to see if there's going to be an aurora up there. It's even an M class, we don't see that often. Okay, so if you're looking at spaceweather.com, you see that the numbers are up at a high level. Here's a spike up into not even into M, but there's a significant amount of solar energy coming in at that spike. There's a
I'm sorry, so the y-axis on the right graph is energy level, and it's characterizing the different bands, A, B, R1, R2?
it isn't exactly energy level.
Okay.
I wouldn't call them bands, those are just metrics to describe, like, you know, a lot or a whole lot or a super whole lot,
Okay.
you know. And
Is there an X up there? My eyes are.
there's an X, well, it's hard to see, it's in the red, the X is in the red,
Okay, it's all right.
which is appropriate because X would be a biggie. And I've been monitoring 24 hours a day, well, not now because my magnetometer is right here, but until yesterday, 24 hours a day since December, I haven't seen anything in the X class.
KP stands for what again?
The K means Kennziffer, which means characteristic digit. Don't ask me why.
Okay.
You know, when I went to college, my parents said you have to study German because all science is done in German. Well, one of the many times they were wrong. But there certainly is a lot of science still done in German. So what does this do to the Earth? What are the effects of the solar wind on us and on astronauts? You know, like I said, we're protected by things like the atmosphere, the ozone layer, and all this stuff is really does great stuff for us, but not for those poor sods up on the space station. I mean, when there is a solar storm, NASA makes them hide in a shielded part of the space station so that they're not impacted by all this radiation. Remember, these are protons and electrons coming in at very high energies. It's called ionizing radiation. You know, it's just the same as sitting next to a nuclear reactor, basically. So it can be very dangerous.
They use lead shielding.
I don't think they use lead. The cost per pound to get something into orbit is like $10,000 a pound. So they use more like Kapton and more exotic materials like that to shield them.
What?
Kapton is a type of plastic that has some important shielding characteristics. If they were still running shuttle, they would sometimes have to abort missions if the weather looked bad, because the shuttle had very little shielding in it. There was in February 2022, there was a solar storm. It destroyed 40 Starlink satellites. I mean, all I can say is yes.
Not like a good start.
Yeah, wasn't that one launch?
I don't know.
Yeah, they were in their preliminary orbit. So they didn't have some part of their orbit that they needed. And they never got it.
It could be, they're all in pretty low orbit. Matter of fact, when we do get a big solar storm, as the particles impact the Earth's atmosphere, it transfers energy to Earth's atmosphere, which of course causes it to heat up. It's important to think, people in physics, we often talk about energy in terms of temperature. And temperature doesn't always mean that it's hot, physical presence. Temperature in physics usually means things are moving fast. The faster they're moving, the higher the temperature. And so as these particles impact the Earth's atmosphere, it tends to excite the Earth's atmosphere and drive the temperature up, which makes it expand. Well, that's not such a great thing for a satellite in low Earth orbit, because suddenly the satellite is experiencing all this atmospheric drag. And in some cases, satellites deorbit as a result of that. In other cases, they have to boost them, like the space station. Space station has to be boosted, regularly, because otherwise its orbit would decay and would fall into space.
So Jack, your K index, when I did the program, I had to do a lot of literature search to figure out what the heck they were talking about too. So your Ken zipper, meaning spot on, but the K index quantifies disturbances in the horizontal component of the Earth's magnetic field with an integer in the range of 0 to 9, 1 being calm, 5 indicating more, and the 3-hour average KP index is the mean standardized K index from 13 geomagnetic observatories between 44 degrees and 60 degrees northern or southern geomagnetic latitude. And that's where it gets into the magnetometers that we're going to talk about.
And I did a lot of digging on this, and apparently they say that the K in this is a quasi-logarithmic scale. I can't figure out what that means. I've looked everywhere. Logarithmic means that basically, if you change something by a factor of 10, that's basically 1 log. So like we talk about the earthquake scale, the Richter scale is a logarithmic scale. You go from an earthquake level 6 to a level 7, that's a factor of 10 increase in energy. This K scale is quasi-logarithmic. I don't know what the math is behind that.
Maybe it just wasn't developed by a math major.
Could be. One of the other effects that these things can have, especially coronal mass ejection, where we get this tremendous amount of energy being blasted at us. If it hits the Earth, they can be devastating. In 1859, there was what's called the Carrington event, where we got hit big time by a coronal mass ejection. And it took out, it wasn't like today, there was no power system. Right? But they had telegraph lines. Telegraph lines fried. And they were having so many problems that they shut off all the telephone lines, turned off all the power. They still could transmit signals because of the energy coming in from the sun, from this event. What happens is that, this energy comes in, and if you remember Michael Faraday, who brought us the electric motor and generator and stuff, showed that if you take a magnet and pass it by a wire real fast, you can induce a current in the wire. That's exactly what's happening. You get this stuff coming in big magnetic fields, inducing currents in all these wires. If that were to happen today, where we have all these power lines, the power grid, and we have all these communications systems, we would be toast. This is truly a scary, it's gonna happen. Hopefully not for a long time. But this could be a truly devastating event. When the Carrington event happened in the Rocky Mountains, there were miners who were woken up by the intense aurora, and they thought it was daytime. They got up, made breakfast. They didn't realize. It was the auroras were visible all the way to the equator. That's pretty cool, but it would be a kind of a nasty thing for us.
Wasn't the New York blackout in what, 60 something? Wasn't that triggered by coronal mass ejection up in Canada and everything rippled down?
I don't remember, to tell you the truth. I remember the blackout, but I don't remember what
I think
caused it.
so too.
What's
Sounds
that?
familiar.
Mhm.
But that's why it took out, the power grid up in Canada, and just the work back just went out and shut a bunch of things.
You know, one of the things that the defense people worry about is the electromagnetic pulse, an EMP, where you can boost a nuclear weapon up in over a country, detonate it very, very high in the atmosphere. And then what would happen is the Earth's magnetic field would collapse around that event. But then it would reform. And of course, that magnetic field coming up would induce all these same sort of thing into all the power lines and just wipe out power, communications and everything. It's just exactly the same thing, except that sun is not nasty, it just is the way it is.
Where is Carrington?
Carrington is a guy, Richard Carrington. He was a scientist who was the first person to really figure out what was going on back in 1859. It affected the whole Earth. What about auroras? I mean, we think about, this is a picture taken, of course, right here in October. We had that phenomenal event. It was so much fun. We have the aurora borealis here in Australia. In the southern hemisphere is the aurora australis. This is from these electrons primarily coming in, following the lines of a magnetic field around the Earth. That red that you see there is mostly from atomic oxygen that's being excited by them. The green is from lower altitude oxygen that's being excited. And it's sometimes you look at a blue, that's more nitrogen that's being excited by, in our atmosphere, it's being excited by these incoming energy. So what are the effects that you can see? And again, these are the KP numbers that, Lori mentioned, gave the numbers for them. And you can see what the effects you might get at different levels. I mean, at level 9, you're talking, oh my God, this is gonna be bad. But we see typically 3 and 4 all the time on Earth. This is what happened in October, when we had the aurora. Suddenly, the KP went up to over 8. And as a result, I mean, we could see the aurora just outside here. It was incredible. Unfortunately, it's been kind of boring since then.
So what did it actually do? I mean, other than spike, what were the practical effects on Earth?
The only real practical effects was that, that we could see were the auroras. They had problems in space. The astronauts had to hide out in the space station in their safe room because of all this energy coming in. The atmosphere expanded, so they had to boost satellites higher up because the atmosphere was, causing drag and bringing them down. But there was no, to my knowledge, no effect on power lines or anything like that. So how do they measure this stuff? Well, it's largely measured through magnetometers. I've kind of been playing with this idea. If you run a magnet or a magnet near a wire, you get current in the wire. You move current to a wire, you will generate a magnetic field. The two are totally interrelated. And so they use magnetometers, and all they are doing is sensing the Earth's magnetic field, strength of it. These are done all over the Earth. And this data is recorded constantly. This is some data from a bunch of European magnetometers. And you see all of a sudden, oh my God, crazy stuff going on. That means there's a lot of energy coming in from the sun. These particles are coming in and disturbing the Earth's magnetic field. And so we're very unsophisticated with a simple compass, which is not sensitive enough, but if it were, you could actually detect that because this compass merely detects the Earth's magnetic field, which is what any magnetometer does. And Laura's going to show you a very cool variation of that. But if you can detect the Earth's magnetic field with great sensitivity, then you can detect these solar wind, these solar effects.
Jack, can I?
Yeah.
I'm
Sure.
You lost me.
I'm sorry.
I understand that if you run a magnet across a wire, you detect a current, or if you, or reverse. But how does a magnetometer?
So the
So I mean, a compass, it would actually deflect. If there was a change in the magnetic field, the compass would deflect.
Correct.
So the graph on the left, I assume is showing, is it a current deviation?
Yeah, that's a good question. The way a magnetometer works, it's basically a coil of wire. A number of many turns,
Okay,
and if nothing is happening with the Earth's magnetic field, there's no output. No change means no output. But if the magnetic field near that wire changes, it generates a current. So if the Earth's magnetic field is totally stagnant, doing nothing, but you rubbed a magnet near it, you see all kinds of effects. Okay, and it's the same.
I'm sorry, you see all kinds of effects in if you rub the magnet near the coil.
You see voltage coming out. of it.
Okay,
If you take the magnet away and the Earth isn't doing, the Earth's magnetic field is quiescent, you get zero voltage.
Okay.
But then as the field does change, you get some voltage, not much. It's very minimal effects.
thank you.
Now, the magnetic field is in X, Y, and Z, right?
Yeah, get to that.
Okay.
Very good, please. How big are these things? You know, how do we measure this stuff? The Earth's magnetic field, or all magnetic fields, are measured in either Gauss or Tesla. The Earth's magnetic field is a couple of Gauss, which is a very small number of Teslas. You're talking about nanoteslas. Okay, it's a very small number. But if we look at this event, for example, with some magnetometers, this scale is 200 billionths of a Tesla from there to there. And so it gives you a sense that, yeah, there's a change. If the Earth's magnetic field is normally around 50 nanoteslas, this big event was, I don't know, 300-400 nanoteslas. It's a big change. Big change. We can detect this stuff. If you go to this website, you can monitor all the US Geological Services magnetometers. There's a bunch of them. And you can actually input what data you'd like to look at. So here's the FRD magnetometer is in Virginia. I use that one because that's the one that's closest to us. So it'd be correlate most clear and cleanly with the data we take here. And they update this constantly. I mean, minute by minute, it's updated. So if the Earth's magnetic field is quiescent, nothing interesting going on. It varies. Okay, magnetic north is not the North Pole. The magnetic North Pole is in the Hudson Bay. And as you move around on the Earth, you'll find that the true north or magnetic north is a little different from true north. So right here in Maryland, magnetic north is about 11 degrees west of true north. If you go up to Newfoundland, it's about 25 degrees west. If you go to England, it's like 5 degrees east. And you can detect that with a compass or with a magnetometer. And that's going to be useful for understanding, what the fields look like.
And what's interesting with all that is both Jack and I know the statement, true virgins make dull company, which means that you have, when you're taking compass readings and magnetic readings, you have to correct for magnetic variation, and depending on where you are in terms of your latitude on a sailing yacht, it'll be more as you get further north.
Or if you set your telescope out outside here tonight, and if you align your telescope with magnetic north with your compass, you're not going to be anywhere near polar aligned because it's 11 degrees off. Set your phone to measuring true north, not magnetic north, when you do that, because it's a substantial error. You'll go.
Dwight hiking maps, those topographical hiking maps have a little compass rose thing that tells you how much for that date you need to adjust for where magnetic north is gone.
Absolutely. And so Al, to get to your point, yeah, the magnetic field, obviously, the Earth is not flat, right? So the magnetic field has an X direction, a Y direction, and a Z direction. And you can measure all three directions. As a matter of fact, I'm gonna show this magnetometer in a little bit, but magnetometer has 3 coils on it. One for each of those 3 directions. And the most interesting one is often this, which is it's the difference between the X and the Y direction. Because that is a deviation between true north and magnetic north. And that's one of the ones that I find gives me the best data when I'm looking for solar events. And on the right, that is a very fancy magnetometer you probably have in your pocket. iPhones have it. You know, and there are these applications, there's one called Physics Toolbox that gives you access to all 3 axes of the magnetometer in your phone. I mean, way cool stuff. If you twist the phone, you'll see these kinds of graphs happening. And I think, Lori, here is your chance to take it away.
Okay,
Good job, Jim.
so far, he's coming back. So, through the Astronomical League, I worked on one of their newest programs called Space Weather. And it was fortuitous that they started the program last summer because we have the solar max that during that time hit. And in order to do it, they send you or have you download some directions on how to build a homemade magnetometer. I think the whole thing may have cost me $5 or $10. And that's because I didn't have a suitable magnet and I had to order one from Amazon because I was too lazy to go to the hardware store. This is my magnetometer. Do you like it? So
I like it. Pretty cool.
thank you. So I've got these beautiful purple rocks in here and a couple shiny ones, just because I figured if I had to look at it for 100 observations, I wanted something shiny. I am a girl, so I like shiny. I have a couple little stars on here that are glow in the dark. This magnet has attached to it, and you'll notice if I turn this bottle around, that the mirror side doesn't really want to show itself to you. And that's because it's a polarized magnet and it is sensitive to the poles of the earth. But this is essentially a magnet with a mirror on one side and a part of a 3x5 card on the other side. On the top is a straw so that I could run a thin filament through it to hang it down into the bottle, which I had to cut open in order to do this and then weight it. And as I went, I found the need. I also had to tape it, but not to the floor in my basement near the sump pump, which has a magnet. In some planetariums, they were discovering that theirs a little too close to the roadway. When a big truck would go by, that metal magnet influence also influenced the magnetometer. So I ended up with 2 different places in my house. The second one is what got me through the remainder of the 90 observations. I had it on a wall that was underground, cement floor, taped. I had my my fancy mason jar hot glued and taped to the floor. I had some popsicle sticks here where I could line up my laser pointer because I knew that the laser pointer was going to need to get recharged a couple times during this. So basically, what I had to do then was once I got a nice firm place that wasn't going to be influenced by stuff. I also put up cardboard walls because I have cats to make sure that they weren't going to get interested in this. And then I put along the wall measuring tape. I had to then set this up so that when I turned on my laser and I had this all set up specifically in this, so it would be in the same spot every time. Now you'll see that this laser is actually moving back and forth, and I'm gonna point this down so that folks on the call can see this laser going back and forth. This is this is about the distance I had in the basement for between my mirror and my measuring device. So you can see that this mirror, because I picked it up to show you that it was influenced by the magnetic field of the earth, is needing to settle down now. We'll come back in about 20 minutes and it will still be moving back and forth. So I would have to take my Fitbit with its magnet and put it behind my back, creep down my basement steps, sneak up on this whole contraption. I actually had to break the wooden pieces that were taped to the floor so that they weren't attached. Very, very gently turn on my cat toy, my laser. And hope that in that set of movements, I had not caused this hanging mirror and magnet to move much. The reason is I didn't want to stand there mesmerized for a half hour or to have to come back while the dot settled down to end up on my measuring tape to tell me what my number was. The number itself didn't matter. I just needed some standard measuring thing that each time I went to measure it would tell me that there was a difference between it was on 25.5 inches this time, and now it's on 25 and 5/8 inches this time, as an example. As the magnetosphere was affected by solar winds, I would actually see and be able to plot the changes as measured by my ultra high-tech soda bottle with its pretty little rocks and my cat toy against my sewing measuring tape, and with assurance comparing it to the websites that Jack was showing you earlier, was able to say, hey, there's something going on, time to look outside, which for the time, the 100 observations, the 100 days that I was doing the program happened once, which was fine. This is a picture of some of the one-page art that the Astronomical League, in particular John Goss, past president, puts together to show the different programs to kind of, let people be aware of it. So this particular picture is not only showing this lovely state-of-the-art soda bottle, which is actually left over from a holiday party 2 years ago. Nobody wanted the caffeine-free Diet Coke and it wasn't suitable to drink, I think. Anyway. And they had you go to these different websites that have these graphics, download them, put them on your log page, measure what your magnetometer had to say for that day. And then I took it a step further because I thought, well, that seems kind of unsatisfactory. And it was the beginning of the program, so they didn't have a lot of data on people doing it yet. I went and compared it to the Sweden magnetometer. Why Sweden? Well, as I was learning through the program, I knew that was a little too far away. Jack, of course, has found the USGS sites are closer, but the Sweden one gave me numbers that I could plot on the same graph as the numbers that I was plotting for my sewing tape. So I had something that was apples to apples. I could compare so that I would know, are the numbers that I'm getting from my state-of-the-art beautified blue tape magnetometer telling me something useful? The answer was yes, because when my magnetometer spiked, so did another magnetometer in the world. Now, it's a bit of a distance to get to Sweden and the latitude is different, but there was enough of a comparison there that I kept using it for the duration of the program because it was working for me. And I got program the award #1 for being the first one to turn it in. But anyway, questions on this part?
So, when you crept downstairs and did your Fitbit, the light would have been stationary. But if an event would have happened, there would have been a deviation from baseline or base point.
I think I understand your
I mean, I'm
question.
just trying to
So-
understand.
I crept downstairs so that I wouldn't do anything
Right.
to shake the mirror, so I wouldn't be
Like,
doing this.
Exactly, so it would be
So-
a-
I would do one measurement a day. And we know that that's not enough data because Jack's going to show you some really cool stuff with his data. But I would know the difference between today I'm at 26 inches. Yesterday I was at 25 and 5/8 inches.
Okay.
Oh,
So-
there's almost a ½ inch difference here. Did the inch matter? No, it's just a number line.
No, they're
It
different,
was something I could then plot, and I've actually got a copy of it, if you want to see the plots, I can show you that afterwards. But I had something then to plot to say, there's a difference between yesterday and today. Now, what does that mean? We're going to pull the data from the sites that they have you pull, and, okay. So during that change, I had a spike in the KP index. And so this setup was able to tell me enough information to know when to look up. And the cats did get their cat toy back. That was a good question.
So Lori, which governments or which entities internationally are taking regularized data other than the Swedes? Who in NASA is doing this and elsewhere? Are the Russians and Chinese doing it? And
Well, from memory, I knew there was one in Japan. And actually it's NOAA is the government agency that oversees this part, although NASA, of course, has cooperative agreements because they need to know when the astronauts need to go in their room.
right,
But all across the world, there are governments that are interested in this for all the same reasons. And there are a good number of these different magnetometers across the world. So I just don't remember off the top of my head which ones, but I know that these sites show you in real time what their magnetometer readings are. So that's how I knew that they existed, because I saw their data.
so let's just take a scenario. So all of a sudden, somebody at NOAA recognizes that that there's a KP variation going on. So then immediately they say, oh, the astronauts, we're having a solar flare, we're having some solar wind significant solar wind activity. The astronauts need to retreat to the safety zone. And so it would be after noting that there were some anomalies and variations going on, and then so it would be reactive. Wouldn't be predictive, it would be strictly reactive, right?
Yes and no. It is very much science that's in its early stages of learning how to predict it. That KP index is one way that they're trying to do that. So when I was reading off from my sheet about this being a mean, capturing that data and then running an average on it is a way that they're using to try and predict what's that like 3-hour window is going to look like for this. Now, I think it was one day last week, we had a prediction of, oh my gosh, we could have aurora or something. It was last Wednesday because we were at the tri-state meeting. And as the evening went on, it started to go to sunset, we're watching this KP index fizzle. So just as much as it had come up, it had fizzled. So those predictions weren't very valid. They weren't like weather predictions. The other thing to look at is the websites for these circles. These aurora circles will be around the north and the south poles. They will also have the heavier part of the circle in the direction of nighttime. So I don't know if you can see across the US here, it's nightfall. for Maryland, but not yet for West Virginia. And in this case, you see with that line of nightfall, that this greater green area is on the night side of that. So you get more of this predictive circle that appears in that way. And then now you start to see people put out pictures that show the aurora and what you can maybe pick up with your eyes, and then another circle for what you can maybe pick up with a camera. But it's more art than science, so they don't really have it set to know that this is the radar for a thunderstorm and you're going to get wet in an hour. That kind of predictability yet. The science isn't there yet.
They actually look at the CME too, though, and say, hey, there's a CME, so we expect it to get here in a couple of days.
Not only that, but even in this AL program, they give you a range of a window of how long it takes solar wind to get from the sun to the earth.
Or a change in.
And
solar.
depending upon what that ejection material is, the speed of that solar wind is a little different. And off the top of my head, I seem to remember it was like 2 to 5 or 6 days. So you can have something coming at you pretty quick, and in 2 days it's here. Now we know it's 8 minutes for photons to get from the sun to here. That's the speed of light. So these solar ejections are happening, the solar wind is happening at a much slower comparatively speed than photons. But there is quite a variance in that amount of time before it hits. But yes, they look at sunspots, and some sunspots will tell you that they have a lot of that X layer of that X can't think of the word. Stuff coming at you that's far more potent. And if it's pointed right at us, we stand a greater chance of getting it. But as Jack was describing, we're this teeny little blue dot, if you will. It could go above us, below us, to either side. We could even, in our solar, in our orbit around the sun, be running into it. Because everything's continuing to move. Any other questions? Let me see if there are any online.
I think you have 2 more slides.
Oh, hey, one other question. So how do you know your rocks that are sitting underneath in your soda bottle there, that they're not ferro nickel, magnetic stuff? Are they, do you know what the chemical content of those is?
That's a great question. And I was taking at face value what the wrappers had said from when I originally got them as decorative stones. So it's actually some glass and some rocks.
So they're not samarium magnets.
They're not meteorites that are high in iron content. But if they were, then in plotting my data, I would have seen that something was up, because I wouldn't have had those fluctuations. And it would have caused me to go, wait a second.
Fluctuations, you wouldn't have had the fluctuations because they would have exerted such a
An
strong
influence on it, yeah.
influence that it would have stayed, much more rigid.
I assume that. That would be my assumption going in.
Well, that's how you figured out you were near the sun.
That's how I figured out I was near the sump pump. Like, why is this not? Oh, well, there's a sump pump in the corner. I was 3-4 feet away from it.
Yeah,
I went to the other side of the basement, so.
well, that was smart. I mean, but who figured it out that the sump pump was affecting it?
I assumed that it was affecting it because I was looking for any kind of magnetic interference.
Yeah.
And there was none, except for there was a sump pump, and I know enough about pumps to know that there's a magnet involved.
Interesting. Well, how often was the sump pump kicking on? Because it wouldn't affect it unless it was actually on, or would it?
Depends on the motor. If
Huh?
the motor has permanent magnets, then
So if it's moving, right?
If you have permanent magnets in the motor, you make electric motors with actually electromagnets, or you can make them with permanent magnets. Correct?
Yeah, I mean, if you have
So-
permanent magnets, then it's gonna be a constant offset. So it will give you some bias, but it wouldn't be changing.
Right, you
You're
leave the
looking for
magnet
change.
near your device.
But it might be so strong that it would mask any.
My
Nano
first-
Tesla
That's
change.
right, yeah.
My first 10 days of collecting data yielded unexpected results. I'd have to go back and look at my graphs, and that's what clued me in to look around. And once I moved it away from that potential magnetic source, I assumed that's what was doing it. Since it was working after that, I chalked it up to a learning experience, and they didn't deduct 10 observations off the program for my learning. Because I identified it and spotted it as an observation.
So did you just notice that your needle was not going through north? Or did you notice something in the daily changes?
Michael Faraday would be proud.
I noticed that my magnetometer was not moving the way that the one in Sweden and the one on the spaceweather.com were moving. So when they peaked, mine didn't. Mine stayed steady. And that's when I started looking for some kind of magnetic influence. And then once I found, or I changed my setup, then my results were very much peaking when the other ones that I was using as a control, when they peaked, I was peaking pretty closely. I mean, for as crude as this technology is, it was, in my opinion, close enough to, yes, there's a definite change there. But nothing like what Jack has, I'm sure. Are there any other questions? And I can,
I think you have two more slides. You sent me two more late in the game.
okay. I did, yes, so, okay. So these are pieces from the program, and in particular, all the programs from the astronomical, week. By the way, I like to print them on half pages when I want to print them out, save a couple sheets of paper, maybe a ream in a lifetime, I don't know. They usually tell you right off the bat how many observations you need, what kind of instruments, if you have to make it yourself. And what observation requirements there are. So that's what these two boxes are. And they leave it up to you most of the time to use your own imagination for what you want for a log sheet. My log sheets included some background data because I knew nothing about this solar weather thing. It just seemed like a kind of a cool thing to do because you can do it on cloudy days too. So I ended up doing a page per day, and out of all of the things that they ask you to go and download, and including your blog page, I actually added a couple things in here. I found it interesting that there was this disturbance storm time index thing, because whenever something spiked, then you got to see this red zone thing, and I thought that was kind of cool. They had you download the circle for the pole. And then I also found that this graph here that shows the different kinds of ejection and the magnitude of it was kind of interesting. In addition to, they had you download the KPs and the sunspots. The sunspots are numbered too. So if you go to spaceweather.com, it'll tell you, okay, sunspot number, blah, 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 is detected, we're detecting that it's ejecting this X-class stuff. And it's coming right for Earth, or it's ejecting it and it's pointed the wrong way. They'll give you predictions like that. This is actually the graph I was trying to show you in my paper. I'd forgotten to give in Jack this slide. This was sort of above and beyond. I wanted some way to know that my data was meaningful. And the program coordinator thought that was kind of a good idea. So this alone wasn't enough for me. I wanted to know, does this soda bottle really tell you anything? And plotting this out for myself is way. So, my data is the blue line. And remember, I'm using inches on a scale, so I could have shrunk those down. The orange is from space weather, and this gray is from the Swedish magnetometer. So very loosely, again, high tech here, you can see the spikes are happening at about the same time. They weren't that first 10 days of this. Now, when things went bananas, we had the KP index around 8, this is in October. And then these are pictures that were taken out front here at Bear Branch. So that's the real-time result. And in fact, here, this is right overhead, kind of looks like fireworks when it's right over your head. It went clear from the north overhead and over the nature center from the grassy knoll. The nature center is south of where you are on the grassy knoll. I got some pictures, gave them to Dawn, of aurora over the nature center. I thought that was kind of cool. So that's the same one where they were seeing aurora as far south as Puerto Rico in October. So that's what my log page looks like. Sort of a teeny version here. And this is my basement floor. I've done nothing with it. I bought it this way 25 years ago. But you can see in one end, I have my little cat toy shining on the mirror. And then I have on another wall, this measuring tape. This is a close-up after I put my cardboard wall. Luckily, the cats never found it interesting, so I didn't have to worry about that. But you can see that on the floor, I had everything pretty nailed down with tape, so it didn't move. This is a close-up of my measuring tape. You can see it's real scientific. I even put it upside down so that the numbers, when they went up, would be like a spike instead of going opposite from the official magnetometers I was comparing against. And then, of course, a close-up. The base is supposed to be sand, probably because it's not going to have any kind of magnetic or iron content to it. But I went for pretty, and therefore, you're right, faster I put myself at risk for some kind of interference.
Actually, you gotta be real careful which sand you use. This job, this sand
Yes,
in New England would not help you.
yes, you don't want to use construction sand on a playground either. So when you learn when you have kids. And then you said there was one more slide in
I
here.
think that's it.
I think you're right. Were there any other questions before I give it back to
Good job.
Jack? Here's a fun program.
I just
Thanks.
think it's really cool. Simplicity of your device. You got a long baseline, so you really had a reasonable resolution, right? Like, what sort of angular deflections were you getting? I know you did it on a linear scale, but if you did the math,
Angular
of your
deflections.
needle, of your magnet.
Oh,
You could figure it out from the picture, because those are
No.
12-foot tiles.
Right, you just need to know the
Yeah.
baseline and comes to trigonometry.
yeah, so the floor tiles, there's it was about a little over 5 feet between the mirror and where the light was reflected onto the measuring tape, and then you can kind of see on the mason jar there where the laser's pointing. And I read later, after finishing the program, that there is a range for what that angle should be. Well, that was real nice after I finished doing the program to learn that, but
What did they say?
I don't remember off the top of my
Okay,
head, but
yeah.
I do remember reading that afterwards.
So like what kind of length reflection were you seeing? Like your measurements, I don't know if they're centimeters or inches, but
Oh.
when you saw an event, like
What was my
how far
range?
did your Did your laser dot move?
Um. Let's see. I also cut off the 20 part and just went with, if it was 26.6 or something, then I just recorded it as 2.6.
Mhm.
So I'm seeing 21 and 875, and of course I converted to decimals. So I think the range, if I understand correctly, on that measuring tape was
The range of your measurements.
great, about an inch. Mm. Inch and a half, maybe, just real quick. Yeah, it wasn't much, and I had to have it the 5 feet apart there to get that much. Obviously, if I pulled it back further,
5 feet from your tape was 5 feet from the mirror. Is that what you're saying?
yeah, see the floor
Baseline,
tiles,
correct.
they're
Mhm.
12-inch tiles.
Okay,
And so I'm just doing a quick count there. It looks like about a little over 5 tiles. So it's about 5 feet away.
Lori, can you sneak back up on that laser and turn it on and we see how much, movement we have now?
And anytime I bumped the mason jar, it was no good either. And in fact, I've got this backwards, but that's okay. And of course, I'm banging the table by moving this, and you can see that that's jiggling.
Yeah,
Yeah.
that's table wobble.
Yes, as I was moving this. Just moving the table.
Do you think it's the metal in the table or is it just the
No, just the
wobble off of the,
vibration.
off the vibrations off the floor?
The movement of this on that tabletop, which is why I nailed the sucker to the floor. We're just like, okay, enough of that.
so quick calculation, 20 degree.
Okay,
Max radiation.
thank you.
Right, your range.
Good, because I was having a hard time trying to make math sense of that. I wasn't a math major, and I think
So,
you were an astronomy teacher, right?
chemistry.
Chemistry, but
Mhm.
still very sciencey.
Little
I do
longer,
science for fun.
little longer magnet.
Good job.
I mean,
I don't know. That's a question for you. Would a longer magnet have more movement?
no, because what determines you need a longer baseline, you need a bigger basement. Right?
Okay.
Yeah, the longer your baseline is, the more that magnifies the linear movement. Right?
Okay,
It makes it easier to measure. So if you, if you had 10 feet of separation instead of 5, right? And you would still have the same angular deflection, but your dot would move 2 inches instead of 1.
so my peaks would be more visible is what you're saying.
Well, I mean, that's just a scaling issue.
That
But
makes sense.
it just makes it make your measurement more precise. That's,
That makes sense.
yeah, longer the baseline, the more accurate the measurement will be, right?
And
Yeah.
I think
The
it
baseline in millimeters.
would have made it more visible for sure.
Yeah, yeah. I mean,
And I
the
could
the
have,
point of that graph is just that the spikes happen on the same place in time.
right, I wanted to see if I had
Yeah.
meaningful data. The changes that I was observing were meaningful and not something else.
Yeah, that's cool. Very cool experiment.
What I love about this stuff is it's like a 11th grade science project where we use low-tech materials to prove out a proof of concept. And,
Take care of.
you know, it's cool. It's just cool. So,
So according to NASA,
And then teachers have the Bible laser.
a lot of these NASA teacher things give you the grade levels that they equate to, but these don't. Anyway, I printed these out and brought them tonight in case anybody was real interested in the nitty gritty, and here's,
is your gut feel that it would be middle school or would it be high school?
I'm guessing high school, but I don't know. So there's your angle of deflection and stuff. And I really love that I'm still learning about it. Any other questions?
Good job.
Save it for Jack.
Thanks, Lord. You know, the cool thing about that experiment is this laser is an amplifier. You're talking about very small signals. And by using this long baseline, it amplifies a tiny motion of the mirror. And your question is very interesting. You increase the baseline, you get more deflection, you also get more noise. That's what you always have with an amplifier. So if you tap this, the noise level goes up.
That's a good point. So to your point real quick,
Yeah.
I did notice that with this laser, with the distance I was doing, the more distance I had, the bigger my laser dot was. And therefore, the harder it was to measure where the center of my dot was, which might be why, just thinking back to last October, why I stopped at about 5 feet. But that's an excellent point. Thank you.
So. Oh, there we go. So this is another kind of a magnetometer, and this is one that I put together, but I cheated. You know, Lori actually built her thing. I went out and bought this board. It's for $25. And what it is a 3-axis magnetometer. And it has, as I mentioned earlier, the magnetometer is basically a coil of wire. And so this just detects all 3 axes. Each of the coils is on a different axis. And there's also a microprocessor on the board that sucks in all the data and makes sense out of it and amplifies it and does some stuff to reduce noise. And I also put the top blue board is a little microprocessor. It's a Arduino. They're, you know, I forget what I paid for it, $10 or $15. I mean, they're very, very, very inexpensive nowadays. That's this board here. Okay. And you know, as I mentioned, there's a coil on each of the 3 axes. And this is the schematic. It's a very simple thing. It looks like it's a bunch of pieces and stuff, but it's just this board plus that board and a few wires. There's also, I put a switch on it, which you can see this switch up here. And the deal is, I've got code running on the little Arduino, which is reading the magnetometer, you know, constantly. But it only outputs data about every 3.5 minutes because the data is very noisy. So it's averaging the data. So I average about 1 million data points and then output that to a USB that goes to my PC. And that makes the data a whole lot smoother and cleaner. So, and this is the kind of data that I typically get in this thing. This is, I actually, this is a little program I wrote to run on the PC that sucks the data in from the USB and plots it. And the, in this case, the red is the data from my magnetometer from this guy. But every time it gets a data point, it goes out to the web. It goes to the Geological Survey site in Virginia. It gets their data. And that's plotted in blue in this case. And you can see, you know, there's a pretty decent correlation. I mean, one of the things, I mean, Lori showed you her data against Sweden. Well, it's a big Earth. Things are different in Sweden. So you're not going to ever get a perfect correlation. Now, there's an awful lot of variation in there. This is data plotted from, I forget why I put that up there, actually. This
Now, those ranges on the top left one there,
Yep.
you're showing between 9.3 and 9.9. So was this data from the October event?
No, this is data, I took in March. So what happens is this graph shows 3 days worth of data. And then the data pours off the side.
But that's like, we're usually in the, what was it, the
KP of like 4 or something like that. I mean,
yeah, I mean, those are high numbers. Those are KP numbers, right?
well, these are actually, this is the angle between true north and magnetic north. That's what
Oh,
it's like.
okay.
And you see that's a little bit different from the 10s that from the Virginia magnetometer. I just didn't have it lined up perfectly. You know, if you twist this, you're going to get different, you know, true north. This is the technique, you know, magnetic north. If I
Okay,
aim it this way, I'm gonna get one number. If I aim it this way, it's gonna be a whole lot different. But the interesting thing is not the absolute numbers, but how they correlate. You know, my data versus the geological survey data. And also this program also logs all the data out to an Excel file. And so I've got, I think about 50,000 data points now since the beginning of December.
You're about due for an aurora.
That's, I haven't gotten any really great data. It's driving me crazy. Now you see this variation going up. If you look at the dates down here in times, that's what's called the diurnal variation. The Earth's magnetic field varies over the day because as the Earth rotates, the sun is exposing different parts of the Earth's magnetic field, you know, is being impacted. So if we're on the night side, we're away from the sun, the Earth's magnetic field is very different than if we're facing the sun. Or the magnetic field for us here, where we're sitting. I don't know if you remember one of the earlier slides I showed had a picture of the Earth, the magnetosphere, and it's like streaming off. There's a bow shock with the sun here, the bow shock, then it streams off. As the Earth rotates, that varies. And so that is that's the diurnal variation.
So your tall peaks are local area and
Yeah, yes. I'm not sure if I can demonstrate this. What do I do to go to a different screen? I don't want that PowerPoint.
You can stop, share,
Okay,
and then you can share something else.
yeah, how would I do that? I can't deal with technology, man.
It's okay. I'm just doing it to make me feel useful and sure.
I noticed that the diurnal variation between the two sites is quite a different scale.
It's different,
But
but
yours is about twice as much.
yeah, and you know, I'm not in Virginia, and the sensitivity of this is probably a little bit different.
Mhm.
So if I go to,
So now you want to share something else.
let me I've started this program. And this is a very complicated program. Takes a minute to do that.
Yeah, it's Python.
So can I share the whole screen?
Yes, so if you go back to, click on the screen for the Zoom,
Zoom here maybe?
that works too. And then click on share,
Sure.
and then you can just share the screen. And then anything you flip through will be shared.
Okay. Oh, there we go. So
You can maximize anything you want to show bigger.
So this is actually collecting data. Now, this is, the blue is data that from my, it loaded old data from my Excel file that it kept. The red is data that's being taken from this magnetometer now. It only updates every 3.5 minutes, but if I flip the switch, it updates much more rapidly, so I can line it up with true north and whatnot. If I look at this screen, that is the raw data coming back from the magnetometer. And so, let's see, we've got this column is the X, Y, Z, and I think that's the variation, and there's some other data I'll get to. But if you look as I twist this, okay, now you can see, look at that first number, how much has changed. Because I've twisted and it's detecting the magnetic fields differently, it's detecting the fact that we're not pointed north, or as close to north anymore. So that's sensing the Earth's field right now. So I mean, if anyone is,
So X is north, Y is geographical east, west, and
yes,
Z.
Z is, and Z is actually interesting because sometimes there are big solar events that will make a big effect on the Z. A lot of the professional sites monitor that. And so I log all that data to my Excel file so I can analyze it later. Go back to PowerPoint. Any questions on this?
Okay, so you conceived of all that stuff yourself.
Well, no, actually, there's some, there's a guy who wrote these books here, who has come up with some of the code that's in this, in the Arduino.
Some of the code,
Yeah, I did some stuff to it, but they did that. I did all the other code.
but the basic concept of how to put that circuit board together, you have from your prior experience, or you got that out of a science journal.
Well, no, it's, you know, it's just a one computer board and the one magnetometer board. It's nothing, you know, there's really nothing to it. You saw, I showed you the schematic. It's just like 5 wires connected. It's a very simple arrangement. I mean, there's a lot of code. If anyone wants the code, you're certainly welcome to it.
So what prompted you, Jack, to wanna put this board together and take these measurements?
Oh, you were the inspiration. You're the Coke bottle version. I thought that was way cool. I started reading more about the solar weather and its influence on the earth. And I came across some of these books, which gave me a bunch of inspiration.
The chip that's the magnetometer, I think you mentioned it was like $25. That's built as a magnetometer. That's a commercial thing.
It's built and sold as a
Okay,
magnetometer.
okay,
All you do is you put power into it.
yeah, and then.
And it gives you
take it
data.
out. Okay, I guess those 3 sets of coils, each oriented 9 degrees from each other in X, Y, Z. I have to believe that they're very, very sensitive.
Very.
So, like, Lori had to worry about her cat. How, you know, that thing sitting next to your computer, isn't there enough, excess electrical field from your computer that
Good
screws
question.
up with that?
Yeah,
That's a huge problem. So when I actually run this at home, I have this on a long USB cable to the far side of the room, which is unfortunately about 75 feet from the street. And so if a big truck goes by, I see it.
So you don't have cats?
I don't
Are you just
have
doing it at street level? I was doing mine underground.
Because these, but just the way the difference is proportional to a 1 degree difference, a deflection in the mirror. There's a very, very tiny, I mean, nano Gauss or nanoteslas.
Yeah.
But we're even that modern equipment can detect that.
Well, the thing that's amazing is that for $25,
Well,
you can get something that detects.
or $10 total.
Exactly.
Yeah.
Exactly. And I mean, if you look at this, there's a lot of noise.
Right? Technology's
Yeah.
cheap.
Yeah, well, I don't.
You know, TI last week came out with a microprocessor, 32-bit microprocessor for 16 cents. Things have changed. You know, there's a lot of tech available for really cheap prices. This is a golden age of electronics. If you want to play with this stuff, you can buy these Arduinos for nothing. They're very simple to use. I mean, they come with these development environments that are very straightforward. It's amazing how
so your data was the blue data and the NOAA data was the red data?
my data is the red data.
Yours is the red and blue is,
Blue is the
Geological survey.
geological survey,
whose?
geological survey,
They're a subsidiary
US.
of NOAA.
Okay, out of where?
Virginia.
Okay, which is like Norfolk?
No, it's
Is it their
no,
headquarters?
it's somewhere like near Farmville, somewhere out that way. It's
Out-
sort of
out in the
middle of nowhere.
country.
Yeah, middle of nowhere.
Yeah, all right, but you know, I'm looking at the curves and everything else, and you look to me have the 90% plus correlation there. And then some of it, it's like 95%. But I'm gonna say overall, it's 90%, isn't it?
It's pretty close, and I've been able to detect some interesting flares from the sun, but nothing dramatic. I'm waiting for, you know, something like we had in October and make things go off the scale. But you know, we are at just about at solar max now. They think that maybe we just passed it. And the rule of thumb seems to be that you can have significant events for at least a year after solar max. So we could be seeing auroras, you know, for a while yet.
Did you see anything on those Z-axis?
I do get to see stuff, and I haven't shown it here, but yeah, I don't see it as dramatic as I would have expected based upon what I read. But sometimes when there's a flare, I do see a drop in the z-axis as well. Now, that's not the only thing you can do. I mean, this is cool stuff. So I read about this other effect that the solar weather has on our environment. These protons and stuff coming in and hitting us from the sun hit, of course, the ionosphere, this high level part of our atmosphere, which is composed of charged particles, ions. And as you know, an ion has got a charge, proton's got a charge, it comes in, bam, it causes an effect. The ionosphere actually can move up and down quite a bit. Well, it turns out that there is a group out of, I think it's out of Stanford, that monitors the ionosphere for these disturbances to try and correlate that to weather, solar weather. And they call this sudden ionospheric disturbance detection. Let's see. So what happens is the yellow is the ionosphere. You've got a transmitter on Earth. Does anyone even hear a ham radio operator? Okay, well, with ham radio, one of the things we do at the lower frequencies is you can talk to Australia. How can that be?
Because it's bouncing off the
Yeah,
atmosphere.
it bounces off the atmosphere, bounces off the
Well,
ground, it's bouncing off the ionosphere. Well, you can monitor, it's a broadcast station, and it's bounced off the ionosphere and see how the variation signal level correlates then with the change in the ionosphere. And it turns out the US Navy has really helped us out with this. They've got a radio transmitter in Maine that broadcasts to the underwater submarines.
yeah,
All kinds of top secret stuff. But, and I don't know anything about that, but they broadcast a carrier, it's always a radio wave, at 24 kilohertz, millions of watts. And so I built a thing to monitor that. And that's sort of the second half of this thing. This is just a radio receiver, basically, and it's tuned to the 24 kilohertz radio station in Maine, that's broadcasting submarines. And I've made this antenna, which is tuned to pick up that station. And this is actually an analog circuit. Okay, but the output of it is basically a voltage that tells you how much signal I'm getting from that station after it bounces off the ionosphere. Being in Maine is too far away to pick up by its direct broadcast. I can only get it if it does a bounce. And just to make it easy, I took the output, this analog output, and fed it into my magnetometer processor, because I have an analog input on this. There was one that was just free. And that's part of the data that's being sent over USB up to the PC. And I showed that graph earlier of the magnetometer data. Turns out this program that I wrote, I can tell it what data to display. And so by typing in a command, I here told it to, on the red, display my magnetometer, and on the blue, display the output from the sudden ionospheric disturbance detector. In other words, the strength of the signal I'm getting off the ionosphere. And you can see there's a big dip right here, which correlates pretty strongly with the red, strong or stormy weather from the sun. This is I forget what observing word this is. 24 kilohertz. So again, it's a very simple thing. It's only a few dollars worth of parts. And I don't want to intimidate anybody. Anyway, I'll show you the schematic. It looks complicated. These things are just amplifiers, these little triangles. You know, that's these two parts. Each of these little ICs has two amplifiers in them. That's all it is. And a few resistors and capacitors. And the output, so the antenna goes in here, this detects and amplifies the signal, and sends a voltage out, which goes into the Arduino microprocessor, then up to my my PC.
Just to dovetail on that, there is this NASA publication, it's a little dated, but same thing that you're describing now.
Cool.
And it's basically high school level.
Yeah, and get some good data. If you don't want to build this, which is about half the fun is building that way, you can go and buy a sudden ionospheric disturbance detector from this site, from Stanford. They actually manufacture these. And this is a little different from mine. The output goes into the audio input on your PC. Okay, so your microphone input. And then they give you some code that then displays it and logs it, so. I forget what this costs, I think it's like $150 or something like that, it's not a whole lot.
What would you want, who would want something like that?
The interesting thing about this is their program is send the data to Stanford. So you're doing citizen science. You're giving the scientists real data. That's pretty cool. You have to build an antenna. That's no big deal. This is up just 150 meters of really fine wire. It's nothing to it. But you can
you're just seeing a changing signal intensity
yeah, and
from
you,
this one source that's constant.
and yes, exactly. And you can correlate that to what the sun is doing.
When you say intensity, what? If it's broadcasting a signal at 24 kilohertz
Yes.
in the radio.
AM signal.
Well, the modulation technique, I believe is top secret, because this is all the commands for the nuclear submarine. But it's a carrier, a constant sine wave.
So, but what? I guess I'm ignorant of the signal of radio waves. What actually changes?
So what
The-
happens
the
is
frequency or
amplitude.
the amplitude?
As the ionosphere changes its shape, at night, it is less ionized. There's
Right.
fewer ions because the sun's not shining on it.
Right.
So there's less signal being bounced back from it. During the day, where sun's energy is creating more ionization,
The amplitude.
the number of volts.
So there's a diurnal
Oh, yes,
cycle to it.
yeah,
Yeah, okay.
noisy. but
And
diurnal.
basically, as the radio waves are passing through, you're shifting the electrons in the air. Vibrating. And that's what you're picking up. Right?
Yeah. The shift, the ionosphere actually moves around quite a bit. So again, if you're a ham radio operator, you love working at night. Because that's when the atmosphere, the ionosphere is very high. And you get a really good bounce off of it.
Apparently they have different names for the different shapes of the radio waves too,
Like what?
like spherics, tweaks, whistlers, and quartz.
And that's if you use this thing going into the audio input on your PC, because you can actually listen to the output and hear all the squeaks and things.
And that's listening to me.
Yeah, well, there are several of these stations around. You can pick the one you want. Maine is the best one for us.
They had one in
Close.
Annapolis, but they closed it.
They closed it down, yeah. Yeah, anyone who was a sailor saw those antennas all the time.
They wouldn't let them tear down.
Those are the ones at Greenberg Point.
Yeah, Greenberg.
They were gonna tear those down, but people up were like, oh, like.
Yeah, they left a couple of them up or a couple of them down.
Oh, they always, yeah, I think there were 5 at one point, right?
I don't
And
know.
I think there's 3 now.
Yeah.
Last time I went by there.
But they wouldn't have been good for this, right?
No, that'd be too
Because
close.
it's too line of sight.
Way, yes, way too close. Now, of course, they would have been broadcasting a different frequency. So we could ignore that, just, be tuned away from it.
Yeah.
And on this board, this control actually tunes, unless we adjust the frequency, gets spot on 24 kilohertz. Let's see. And since we're talking about solar observing, just make a couple of other points that I think are important. If you just have your regular telescope, you can see some great stuff on the sun. You get one of those cheap solar filters. You get the good ones, like from, Thousand Oaks, for example, not the Amazon variety, because you don't know what the quality of those are. But they reduce the sun's intensity by what's called 5 optical densities, 5 OD. That's a log scale. 5 OD is a factor of 100,000. Okay, so it's only a tiny bit of light. But you can see all the sunspots. It's way cool. And you can correlate the sunspots with the activity you're getting on these magnetometers. We've had a very active sun this year, so that's interesting. If you want to go, and the important point here is use good solar filters. Don't scrimp. They're cheap. Even good ones are cheap. Don't get off-brand stuff. Your eyes are not worth being destroyed.
I ordered one recently, but accidentally ordered 3.
Good for you. You could be everyone's best
Put 'em on
friend.
my binoculars.
So in that, on the solar observing photograph on the left, just are the black dots, those are active, or what is that?
Those are sunspots.
Those are sunspots,
And they're bigger than the Earth. I mean, these are not spots.
each one of those.
Yeah, or not all, but many. I mean, these are generally enormous compared to human scales, Earth scales. They're enormous. And you can actually track them if you watch this over a period of days, because the sun rotates in about 25 days. Watch them track all the way across the face of the sun over the course of a matter of weeks, which is pretty cool. Or if you want, you can buy one of these real solar telescopes, like the Luntz. I guess we can still get some Coronados out of High Point. You know, Coronado kind of went belly up with everyone. But High Point Scientific bought all their stock, and I think they still have some of those. But Lunt or Coronado, these are only good for looking at the sun. They use a hydrogen alpha filter, so it's only letting the light in from that one electron transition. But it's not like if you do astrophotography, if you do narrowband, probably you're using hydrogen alpha filters. Those are no good for solar observing. They let through a passband of multiple nanometers. These are on the order of half a nanometer. A very narrow wavelength. It's safe to look at through the telescope like these things. And they pick up the really interesting stuff, like you can see the flares and whatnot come off. And it's dynamic. I mean, over the course of seconds, you see things change, which is way cool.
There are astronomical league programs for both of those. One's called SunSpotter and the other one's H Alpha. I have examples of those programs here if you're interested.
And doesn't the club have a hydrogen alpha telescope?
Yes,
And so it is possible to
A
borrow
Lunt.
that.
yes,
Lunt.
yes. Right now Jackie's using it because she's doing the H Alpha program, but it is available.
You know, if you've never looked through one, it's dramatic. Especially if you put a Barlow on it and really, blow it up. I mean, it's dramatic.
I was alternately intrigued and appalled that I picked up a seventies era Tasco over the weekend. I was looking for 9.655 pieces, and they still sell on Amazon the screw-in sun filters.
That's,
Yeah, on eyepiece ones,
Uh-huh.
that's a lawsuit waiting to happen, right?
yeah.
Amazon is coming out of China, but I found it very interesting. I was like, oh,
I have
Okay.
one that I use as an example of what not to use.
But if you buy the film, you can put a piece of cardboard, make something. I have a wood lathe. I just cut things on my wood lathe, whatever it calls it. And I forget how much, you just bought some, they're what, $20-30 or something.
Yeah, something like that. Like I said, I got one piece of film that's big enough for my new refractor and, but I accidentally ordered 3 of them.
Hang on to it. It's
Yeah, the
Good
price
for-
is just gonna go up, right?
well, not only that, but there's some debate about this, but I understand that the Mylar will last longer than the glass filters.
Oh, really?
Yes.
Hmm.
I was an Eclipse ambassador, and so we would show examples of the eyepiece thing not to use. And I've used the cardboard frames forever until husband got a 3D printer and then he upgraded me, so.
Yeah, well, the miner's pretty tough, because your filter's sandwiched between 2 flexible layers, unlike glass where, got your absorbing layers on something rigid, so it's easy to scratch.
Yeah, and one of the reasons that the real solar telescopes are so expensive is the filter they use is much, it's called an Etalon, and it's much more complex. It's an interference filter with 2 surfaces that the light bounces around inside, it interferes with itself. It only lets a little bit coming out. But the fact that you see such a narrow section of wavelength lets you see all the really fun stuff on the sun. And I just want to give you some resources. These are some books that I have found to be excellent. And I have And here, if anyone wants to borrow them, help yourselves, just I do want them back, but help yourselves if you want to borrow.
I brought a couple on Northern Lights and Aurora, as well as some particular pictures of Aurora that I thought were cool. We went to Alaska last year, and got clouded out until we got to Canada, Vancouver Island. But we got pictures from there. They just weren't the ones we took.
Are those guys Christian Beladrich and Sten Odenwald? Are the, okay, so maybe the first guy's like Russian or
French.
Eastern, oh, he's French?
French, yeah.
And then how about Odenwald?
He
Odenwald?
works right here in Maryland. I've been corresponding with him. Seems like a good guy.
At Goddard,
It's some NASA, I forget which
Yeah.
one.
well,
He seems like a good guy.
oh,
This
anyway,
video we're saying, right, this flare, what time frame is that?
I don't know. I snagged this off the web.
Right, like, is that seconds, minutes, hours, days?
Yeah, something like that.
Yeah.
well, I think this stuff will look great on your Starfleet Academy application, but I still think we have a problem with the age waiver, so.
A CME can be up to over 3,000 kilometers per second. So, I mean, that's happening fast. That's fast.
I bought my, $10 solar scope from China. It's been fun just pulling that out on sunny days, and yeah, it's kind of, you see the sunspots and you can track them day to day or over the course of a week, and it's like it takes 2 minutes to set up. And you look for 5 minutes, and then you're sitting back in the garage and
Aren't
go on with
you,
your day.
aren't you guys a little worried about like, burning out your eyes, because like, God knows when you're playing with that stuff, because you wouldn't even know if you were damaging your eyes, because you think you have protection and so forth, right?
Well, with the solar filter, first thing I do is hold a piece of paper over the eyepiece, make sure there's no pinpricks causing a lot of energy to come out. It should look like, kind of like looking at the moon or something, just not, it's bright, but not damaging bright. And if I don't see any defects on a piece of paper, then I'll look in it.
And you should inspect it every time you use it.
And the other thing is, especially if you're doing outreach, I always tape the filter on the telescope, because if that sucker falls off, it's not gonna be good. Yeah. Any questions, thoughts, critiques?
Good job.
Yeah,
Thank
thank you.
Yeah, it's fun. It's fun.
It is fun.
Both of you, yeah. Thank you for the effort.
Something I
So-
didn't know was that the ionosphere is actually a significant contributor to the Earth's total magnetic field.
I didn't know that. I'm
Yeah, I was reading
surprised,
about that
actually.
last night. I was prepping.
Really?
Yeah.
Because usually you think about it.
Geology background, so,
Yeah.
there's always been that question of what causes a planet's magnetic field, and nobody knows the answer to that. But yeah, that led me then to read, oh, there's this other component of it. And I can't give you like a percent, but it's a significant chunk.
Wow, I didn't know that.
That's
Yeah.
attributable to what?
The ionosphere,
Okay,
so if you take the Earth's magnetic field as a whole, the contribution of the ionosphere, if you took, you did away with the ionosphere suddenly, the Earth's magnetic field would change, right?
right.
So it has this significant effect, which is why you see this variation as the ionosphere varies.
But the ionosphere is getting more and more holes in it. It's getting thinner in general because of the freon and,
That's the
Other-
ozone layer.
huh?
That's the ozone layer.
Oh, that's right.
And it's actually.
So the ionosphere is stable or not stable?
Very
I mean,
dynamic.
it fluctuates as it interacts with radiation from the sun and from space in general.
Yeah, it's moving constantly. The difference between day and night is dramatic.
So you've got in the ionosphere, the particle, all parts of it are charged, right? And so if it has a regular motion, a wind, if you will, right? Moving particles that are charged generate a magnetic field, right?
Right.
So movement within the ionosphere creates part of the Earth's total magnetic field, right?
Right.
You know, what the other 95% is, no geologist can tell you.
Yes, but people always say it's the circulation of the liquid core. Then, but
But we don't know, do we?
I don't know if there's 100%.
Yeah. And I was reading about, or rereading about, fluctuations, but there have been periods of 10 or 20,000 years documented with no magnetic field on Earth during a flip.
The Earth's magnetic field flips every so often, like every couple of
North-south.
minutes.
17,500 years or something, isn't it?
That's the precession of the equinox.
Equinoxes. So do we know how often that it flips?
It varies, but it's on the order of a couple of 100,000 years. And you've ever heard of this guy, Alfred Wegener? He was a scientist back in the early part of the 20th century. He said, look at a map. Africa and South America, they like.
Oh, they
they're
fit
like
together, yeah.
They left him out of the academy.
They did.
Right.
And then what happened was they discovered at the mid-Atlantic ridge, which is where the two plates are separating. That the Earth's, the magnetic field gets embedded in the
ridge.
the lava, basically as the lava cools, whatever the field was, as it cools, gets stuck there. And they find stripes as it flips every couple 100,000 years. So now there's an Alfred Wegener Institute in Germany where they're trying to do penance, I guess, for being so cruel to the poor. Of course, he's dead. Doesn't matter.
Right. But think of 10 or 20,000 years without magnetic field.
Yeah.
We'd be toasted.
We
How
will,
do the birds?
yeah, okay, so the thing is if
Yeah,
that's
Earth
true,
navigation.
if that's true, then that means it hasn't occurred in the last 2 million years, though.
Oh, no, I think it's occurred.
No, it flips.
Well,
Uh,
all the Australopithecus, what did they do? All go underground or what?
Who knows? They're probably buried down there trying to monitor the magnetosphere too.
No, you'd have a large increase in incoming radiation, not like, we're gonna kill all life, but mutation rates would certainly go up.
Right.
Interesting point, yeah.
Yeah, there are biologists who've actually looked at that question. Like what happens during a period of no field. And try to correlate, change, evolutionary change with that. I don't think they succeeded, but there's a lot of species of organisms that use the Earth's magnetic field. They're bacteria that grow a little iron mineral in them, and they use that to navigate. And the same bacteria, when it grows in the northern hemisphere or the southern hemisphere, like orients the magnet the other way.
It's incredible.
Yeah, right. I mean, pigeons have, a little spike of, magnetic mineral in their brain.
We can't find the next town without a GPS. Okay, well, thanks. guys.
Actually, Jack, I don't use a GPS. I just use the sun and then I have a compass. And at night, or if I'm in a city, like a foreign city, I use the compass.
Well, if you don't have a magnetic field, your compass isn't gonna work, and
Yeah.
GPS probably isn't either. With all the satellite.
So we do have some freebies up here, if you're interested in more information. Are there any other questions from the, folks that are online?
Oh, yeah.
Hearing none, I'll go ahead and stop the recording.